All right. Well, welcome to the Coding Stock live chat podcast. I greatly appreciate everyone joining this live chat podcast session. As we're getting started, I'd like to cover the session disclaimer. This live chat podcast and the Coding Stock series does not represent the opinions or strategies of Akzo Nobel International Paint. Additionally, I make every effort to provide accurate and up-to-date information from the global protective coatings and corrosion industries. Despite this care and attention, it is reasonably possible that the content and live conversations within this session may have content that is incomplete and or inaccurate. I am recording this session audio for rebroadcasting and also for a new audio podcast that I will be putting out onto the Codings Talk channel. Before I set up today's topic, I'd like to cover how you can participate in this live session. It's real easy. All you have to do is raise your hand by using the raise your hand icon in the chat menu. Also, please feel free to hit any emoji to let me know how you're feeling about this live chat. The topic for this session is protective coatings for space. Now, over 20 years ago, a company still known today as AZ Technology of Huntsville, Alabama, developed a spray coating system that's still used by the International Space Station. Their innovative spray coating is well known by NASA, the European Space Authority, Association, and space satellite manufacturers, as one of the only space-stable color coatings globally available. Color coatings are important for spacecraft when it comes to identification markers, docking, navigational targeting, and craft emblems. On this audio chat podcast episode of Codings Talk, I'll cover some interesting aspects of protective coatings for space. Let's get into this topic. Companies like AZ Technology are continuously developing new materials, paints, and coatings for use on spacecraft, satellites, and specialized terrestrial applications such as solar panels and observatories, which need to meet important specific customer-driven optical and resistivity requirements. Protective coatings for space application need to be designed to be low outgassing and extreme space stable, and also meet toxicity and flammability requirements. Coating manufacturers all tailor their product properties related to reflectance, emittance, electrostatic charge, dissipative, and a wide range of colors to meet specific aerospace industry requirements. As you can imagine, the growing market opportunity related to protective coatings for use in space has a limited pool of engineering and professional expertise and production facilities for research and development, the production and manufacturing of coating products that meet these strict specifications and technical requirements. Currently, protective coatings for space have a long history of case studies related to exposure with the extremes presented by the environment in space. Many case studies involve coatings that have been applied to optical property monitors attached to the exterior of the historic Russian Mir space station. The Mir Miaposa 1 experiment, the Materials International Space Station experiment, and importantly, attached to the outside of the International Space Station. Now, that case study ran for approximately 4 years, but the longest and still ongoing is the exterior of the International Space Station. That's 15 plus years and still going on. Due to the precision surface preparation and coating application requirement for spacecraft and or related components, equipment, modules, and more, prep and paint shops need to have thick film application capability using state-of-the-art equipment. High volume, low pressure turbine type systems are used to deposit paint onto components with complex geometric shapes. Primary paint application facilities need to be capable of handling components up to 100 square feet, specifically depending upon configuration. Facilities need to be critically maintained, a controlled environment during the prep, painting, and cure with respect to non-coating particulates, temperature, and humidity. In addition, painting facilities typically are equipped with on-site equipment for formulating, compounding, and testing coatings to ensure batch-to-batch consistency and quality in the final product. To complement well-equipped prep and painting facilities, it's important that they are staffed with expert craft workers and inspection personnel, all dedicated to quality. Now, I've spent time talking about protective coatings. Additionally, spacecraft use high-temperature ceramics, with many materials being capable of temperatures of up to 3,000 degrees Fahrenheit. Extensive material testing is important to test protective coatings' physical properties such as adhesion, abrasion resistance, optical properties, which would be related to solar absorption, emittance, reflection, and transmittance, density analysis, and electrical conductivity determination. This material testing is necessary for future development of tailored advanced technical paints and coatings for use in space and other harsh environments. Every space mission brings us immense insight, helping us to advance human knowledge and our capabilities. But it's not only the missions themselves that are advancing technology. Some of the technologies supporting these projects are just groundbreaking. Material science is one discipline that underpins successful space projects. Now, earlier I had mentioned the Mir space station, which launched in 1986. Mir was run by the Soviet Union space program, and it used a little-known surface coating technique called plasma electrolyte oxidation, PEO, to increase the life of components. The Mir project ran until 2001, when the project reached its conclusion. The new surface technology protected components for 15 years in the toughest of operating environments, known as the extremes of space. Now, early space missions provided scientists with a lot of interesting answers, but is often the case, new discoveries lead to new areas of research. Advancing technologies allowed astrophysicists and scientists to pursue ambitious, formerly considered impossible space-based missions. For example, in 2018, the European Space Agency and the Japanese Aerospace Exploration Agency launched a new mission to the planet Mercury. Using two orbiters, the mission involved a comprehensive study of Mercury, studying the structure and origins of the planet's magnetic field. Neither agency had ever undertaken a mission of this magnitude before. The extremes of temperatures, particles, which are highly abrasive due to the solar wind, and radiation. As with almost every spacecraft, lightweight materials, chiefly aluminum, were used throughout the two orbiters. The alloy's light weight helps to minimize launch cost, making missions more feasible, while their strength provides a stable platform for a multitude of scientific instruments housed on board. However, with today's very innovative spacecraft designs, the boundaries are being stretched of what is possible. Engineers are faced with a number of issues with light alloys as they push the use of these materials to their absolute tested limits. Let's talk about light alloy coatings for space. Light alloys have a range of hugely attractive characteristics for spacecraft applications. However, the extreme conditions encountered in space mean that they still require advanced surface modification technologies in order to protect them and enable their widest possible use. To successfully combat these elements, such surface coatings need to offer complete protection from a range of challenges. The first is cold welding. Many of the mechanical problems found in early satellites were caused by cold welding. Even in the absence of heat, metals in contact fuse together in vacuums. Coatings are necessary to reduce contact adhesion in order to defend against cold welding. UV degradation. Externally facing components are prone to solar photon damage. The effects are clearly visible in returning spacecraft. UV rays can change the microstructure of aluminum alloys, resulting in negative impacts such as reducing their tensile strength. Thermal shocks. Materials in space applications frequently suffer severe thermal shocks, either during launch or when they are subjected to highly variable temperatures in orbit or solar system transit. Materials therefore require coatings with good thermal shock resistance and insulation so as to protect thermally the electronics and scientific instruments on board. Since aluminum is 3 times more conductive than steel, surface coatings are so vital. Solar absorption and thermal emittance. Coatings designed to reflect solar radiation will reduce the deterioration impact on spacecraft systems. Coatings with a high level of admittance and low levels of absorption reduces the temperature of materials and electrical systems. In essence, advanced technical surface coatings are needed to reduce light alloys exposure to the hostile environments of space. As a result, coatings had to be found that offered complete, comprehensive protection against any and all forms of space environmental damage to mitigate risk of further consequences caused by other potential means of lightweight alloy failures. White silicon paints and clear anodizing solutions have been deployed in thermal controlling coatings for space. However, those two options provide limited performance within extreme space environments, especially over the periods of time required in long orbit and deep space exploration missions. Now, some of the benefits related to white silicon paints and clear anodizing solutions include high infra region optimization, high stability dealing with harsh space environmental conditions, and that's related to extreme UV, high temperatures, and thermal shock. Extremely good surface adhesion, very low outgassing. They are environmentally friendly in the application process, and the ability with coating application on complex shapes. They also provide best current technology for thermal shielding of exterior spacecraft surfaces. Now, I greatly appreciate this opportunity to present this topic, and now let me take a pause here. If you would like to raise your hand, I can open up your mic and bring you up on the stage, and open up your microphone if you would like to comment on this topic or maybe ask a question. Okay. Now let me talk to you how you can support content like I covered in this session. I've set up an affiliate program with coffeebrandcoffee.com. Now you can save 5% or more off any orders of quality premium coffee, tea, and more by using coupon code COATINGSTALK. That's COATINGSTALK when you're finalizing your order. So please help offset the cost of creating, producing, streaming content like this by visiting coffeebrandcoffee.com and using coupon code COATINGSTALK during your order checkout. Well, on next Wednesday's Coatings Talk live chat podcast, the topic will be Cathodic Protection 101. I'm going to cover just the basics. The next session will continue this new combination of live chat recording to produce an audio podcast like we just completed. So I hope that you'll participate and join in on the conversation around Cathodic Protection 101. This session will be on Wednesday, September 13th, starting at 8 p.m. Eastern Daylight Time. Okay, have a great evening, day, or morning, no matter where you're listening from. Thank you.